Maybe I'll record it later. Yeah, anyway, we're going to focus on undetermined coefficients today, variation of parameters tomorrow. Anything else that works? I don't know what else would work. Guess and check. Good luck with that. Although that's kind of what undetermined coefficients looks like a little bit. So the method of undetermined coefficients says this. There are several reasons why we would use the method of undetermined coefficients. One, it reduces the problem down to a pretty basic algebraic problem. That's the benefit of it. Now, the bad news for it is there's only certain g of t that we can get where this works well. Some g of t, this doesn't work well at all. And it really works best if our coefficients in the differential equation are constant. So they're not functions. Variation of parameters, we can deal with more functions, but it's a little bit messier. Okay, here's how we do this. This is going to be maddening for those of you that like processes initially. What we're going to do to be able to use the method of undetermined coefficients is we are going to look at the g of t. So that's this equation. In this case, it'd be the 3e to the 5t. We're going to look at this part here, and we're going to make a guess as to what the answer might be. Okay? Now, we can use some pretty good techniques in guessing because we know that we're going to be taking derivatives to be able to solve this. What type of functions give us derivatives that will yield 3e to the 5t as an answer? That's a rhetorical question. You don't need to answer that at the moment. But we can make some pretty educated guesses to see if it works. And then what we're going to do is we're going to substitute what we're guessing into the differential equation to see if we can find what the coefficients should be. Sometimes it works, sometimes it doesn't. If we can find values for the coefficients, it worked. Our guess was correct. If we cannot, it is not. It's exciting, right? Guess and check. It's kind of what this one's like. Now, we'll look at some patterns here in just a second. All right, here's what this looks like. The steps that we're going to go through to do this is, the first thing we're going to do is we're going to find our complementary solution. Did I use T in this? Yeah. We're going to find our complementary solution. That's our first step.
Yeah, I have a question.
Uh-huh.
It says it's only used for small GMTs. What's considered small in this case? Like,
Yes. To be considered small is really arbitrary. Meaning, I may just mean not a large quantity of functions does this work for.
what's considered a large quantity?
Well, I mean, like, not every single problem will this work. So certain ones this works better for than others.
Okay.
E of t is one of them.
If you can count the number of, like, the types of solution that it'll work for, it's pretty small.
Yeah. It doesn't work for all equations as
And,
well.
for generally only useful for coefficients or constant coefficients.
Not always.
Not always, but if they're non-constant, it could still work.
Correct. Yes, it could. It'd be a
So we're
mess.
not going to.
We'll use the variation of parameters for that probably. All right. So to find my complementary solution, the first thing that I want to do is I want to set up the homogeneous equation. This should look like what we've been seeing so far. So what do I do with this? R's, find your R's. So my characteristic equation is R squared minus 4R minus 12, which means I get R minus 6 times R plus 2, which means R is 6 and negative 2. So distinct real roots. What does that make my solution?
C1 to the 60 plus C2 to the negative 2.
Yep. So C1 e to the 6t plus C2 e to the negative 2t. That's what we call our complementary solution. So this is part of my general solution, but it's just part. So the next thing that I'm going to do is I'm going to work on the the particular solution. Okay. So what we're going to do, the way we're going to work on this and the way we're going to figure this out is we want to look at what our g of t is. So in our case, our g of t is 3e to the 5t. Knowing that what I'm going to be doing with this g of t is substituting it back in to the function as my solution. So I'm going to call this y, and I'm going to make substitutions back in. Okay? Now, so g of t is this 3e to the 5t. What form of an equation would yield results that will end up as 3e to the 5t?
Any constant e to the 5t.
Okay. So we would say that any constant, we'll call it k, e to the 5t, that when I take the first derivative, when I take the second derivative, might allow me to get something that looks like 3e to the 5t. Do you agree with that guess? So it's not so far off to guess. It's not terrible. It's still a little bit of guess and check. So here's what I'm going to do. If I'm going to call my particular solution ke to the 5t, the problem is I need to know what this k is in order to use this solution. So what I'm going to do now is I'm going to take the derivative. So I'm going to take y prime, which would be, we've got a chain rule in there, so we've got 5k e to the 5t. Yeah? And I'm going to take y double prime. Yep, 25k e to the, oh, yeah, e to the 5t. Yeah? Okay. Now what I'm going to do with these equations here is I'm going to substitute them into my differential equation. Okay, so y double prime. We have 25k e to the 5t minus 4 times 5k e to the 5t. I didn't leave myself enough room. Minus 12 times k e to the 5t equals 3e to the 5t. Will I be able to solve for k? Yeah. So we've got 25k e to the 5t minus 20, so that's 5, minus 12. What did I say? 5 minus 12. So negative 7 e to the kt equals, negative 7k. I lost the k. E to the 5t equals 3e to the 5t. If my goal is to solve for k, what does k equal? K equals negative 3/7. That's fantastic, right? Okay. So if that's k, then what I am saying is that my particular solution in this problem is negative 3/7 e to the 5t. That's my particular solution. Now, go ahead, Jake.
Does that imply uniqueness at all?
No.
Well, we also have to add the complementary.
Correct. It is a particular solution. It is not.
It's not super particular.
Correct. It's just kind of particular. Yeah. It would solidify it more if we have initial values. We could look for things, but yep, I'm okay.
Why can't we just tack on the different equation solution onto this stuff? Why does that work?
Why does it work to just tack it on?
Yeah, like that feels kind of illegal.
It feels illegal. I like that you call it illegal. It goes back to this idea. Ooh, my 3.
Oh.
I don't know, where'd that come from?
It came from there.
From the equals up
Top over there on the
Oh, random. Okay, hold on. Let's group those together.
He's afraid of being right.
It really liked that spot, apparently. All right. So we can say this because essentially what we're doing is we're adding the homogeneous part to the non-homogeneous part. I know that seems trivial to say 0 plus g of t, but that's why we can just tack it on. Because this equation, if we didn't have,
If A is a solution,
It-
B is a solution.
I don't, what is telling me there's no network connection? Is it my iPad? Is it Is it the Apple TV? Well, it's still working, so it can't just be the Apple TV.
Maybe it doesn't require the internet.
It does.
Oh.
We're gonna go with it. But that's why.
Alright, so the YTT is just for the 0 and the particular is just for the G.
Yes.
Okay.
Yes. So then my general solution overall for this particular problem would be to combine my y of t equals the c1e to the, 6t, plus c2e to the negative 2t, minus 3/7 e to the 5t. So this part here is my particular solution, and this part here was my general solution. Hi. Or my complementary solution. Okay, we're just... She could have waited a few seconds. I don't know. But anyway.
It looked like she had more to give out.
I'm sure she was super busy. All right. So that's my solution. Now, we've started with E of t before because E of t is such a nice function in that we know its derivatives and we know its antiderivatives really easily, right? It becomes this nice pattern that we can find pretty easily. So what happens when it's not e to the t? Okay. Actually, before we go on any further, let's talk about how okay, so having or knowing what our complementary solution is will oftentimes lead us to be able to make good choices or guesses for what our particular solution is. Notice we should say we are finding a particular solution, not the particular solution, because there's other possibilities. That's what we were just talking about. Let's go back to that problem that we just did, and let's look at what it looks like when we are given initial values and how we solve it using initial values. So from the front, page, we got our solution to be c1e to the 6t plus c2e to the negative 2t minus 3/7 e to the 5t. So that's from the front side. I'm not going to recreate the problem. It's the exact same problem. What does it look like if we now want to find or use the initial values? What do you think I need to do? Take the derivatives and plug it in. If we start with just the one that's given, because I don't need to plug, I would get 18/7 equals c1 e to the 0t, right? Plus c2 e to the 0t minus 3/7 e to the 0t. 0 would be t. So I've got that one. So really what I have is, let's make it simple. If I add 3/7, what do I get to? 21/7? Well, that's 3. 3 equals c1 plus c2. All right, now let's take the derivative. If we take the derivative y prime, what do we get? Chain, we get 6c1 e to the 6t minus 2c2 e to the negative 2t. Well, that's a fun one. Minus 15/7 e to the 5t. Okay, substituting in here, negative 1/7 equals 6c1 e to the 0 minus 2c2e to the 0 minus 15/7. So we get 14/7, so we get 2 equals 6c1 minus 2c2. It's another system of equations.
It's a nice one.
It's pretty. We can handle that. Always is a very long time, Chandon.
The ones that you'll give us.
No. They'll be pretty enough. Okay, solving this, I would get 6 equals 2c1 plus 2c2, and then 2 equals 6c1 minus 2c2. 8 equals 8c1, so c1 equals 1, which means c2 equals 2. So going back into my equation, now my general equation, c1 is 1. So we get e to the 6t plus c2 is 2, e to the negative 2t minus 3/7 e to the 5t. So that's what an initial value would look like. Not terrible, right? Or terrible? It's not too bad. All right, but let's look at some other examples where undetermined coefficients will work. And I don't want you to write down a whole lot just yet. I'm going to let you finish this part. I'll do the writing to begin with. I'm going to let you make some guesses. That way you don't use all your paper. Okay? All right. If the first step were to find, does anybody need that top part still? Are we good? Okay. Let's all of us find a complementary solution. Okay, but I want you to stop for just a second. Do you notice the beginning part of this equation? It's the same. Notice the difference here is just the g of t. So we already know the complementary solution because this part right here is the same as what we've done before. And so we know from above, from our last examples, that our complementary solution is c1 e to the 6t plus c2 e to the negative 2t. There's no need to repeat that. Okay? So we know that part. So now our goal is to work on the particular solution. Okay. Now here's where I don't want you to write. I want you to let me write, and I want you to think about it. If you were to guess at a solution right now, seeing that my particular solution has to deal with sine of 2t, if you were to guess at a solution right now, what would you guess? Okay, so I heard cosine 2t. Okay, let's try it. Let's say we need a constant in there though, because there will be a constant. So let's, and just watch. If our guess is this, if this was our guess, then when we take the derivative of cosine is negative sine with the chain, so we've got negative 2k sine 2t, and then I'd need a second derivative, right? And you're just watching. I wouldn't write down. So negative sine is negative cosine, so negative 4k cosine 2t. Okay. If we substitute this in, again, you're just watching. We're substituting this in. It's taking me longer than it should. Okay, what happens? Well, we get down to this point where we can combine like terms, and I have negative 16k cosine 2t minus plus 8k cosine 2t. Oops, that says sine. I can read. Just a second. K sine 2t. And this is supposed to equal sine of 2t. Agreed? Okay, so what we might say here is that 8k needs to equal 1 because these two are the same. Thank you. So we might say 8k equals 1, right? That would be the coefficient there. And then because there is no cosine, that negative 16k equals 0. How can negative 16k equal 0 and 8k equal 1 at the same time? Is there a k value that can make it that so?
0.
No, because 8 times 0 would give me 1. Not give me 1. So this cannot work, right? So this guess isn't correct.
Do
Darn.
you have to do this for every guess? Yeah.
Okay, what might you guess now? Sine. Okay, but let's think through the process of it. Sine is going to give me something very similar to this, isn't it?
Yeah.
It's just going to be flipped. So that's not going to work either. Could we go through the process? Yes. So those were good guesses, but they're not right.
Arctangent.
Oh, Lord. Arctangent, no. Okay.
Cotangent.
Arctangent squared.
What if?
Is that not allowed?
Well, you could use E, but it wouldn't work well for
Put
you.
it to the natural log of something that does work.
Yeah,
That sounds terrible.
but it might work.
What if my guess was... I'm going to give these constants different names this time, so I can't call them. Cosine 2t plus,
Oh no.
Oh,
No, no.
oops, plus b.
oh, that's easy.
What if this was my guess?
We're supposed to write this one.
This one might be more advantageous to write. Or you can watch first and write later.
Wait, so how'd you make that guess? It just like guessed out?
I just...
So it could be any equation?
Maybe just a premonition coming towards me.
Yeah, like,
Yeah, I mean, where do we get that from?
yeah, like,
You wouldn't. You might not. But the thought is this. Look at what happened both times when we were doing this. We dealt with a cosine and a sine. But the problem is they had the same leading coefficients because we were taking the derivative of the same thing, and therefore I couldn't eliminate anything. So if I try it this way, watch what happens when I take my derivatives. Oh, hold on. Y prime would be negative 2a sine 2t plus 2b cosine 2t. And then y double prime would be negative 4a cosine 2t. I don't know why sines and cosines always take me a second. Plus, minus, that'd be minus 4b sine 2t. Okay, messy, correct? So watch. I'm going to substitute this in. So y double prime, I have negative 4a cosine 2t minus 4b sine 2t minus 4 times negative 2a sine 2t plus 2b cosine 2t minus 12 times a cosine 2t plus b sine 2t, oops, I lost the t, equals, this is fun, huh? Equals sine of 2t. Okay. Combining like terms. If we look at our like terms here. So I have an a cosine 2t, an a cosine 2t. Oh, I have a b cosine 2t also. Actually, let's keep that together. So there's my cosines. If I combine those, I end up with, that is negative 4a cosine 2t, and negative 12a cosine 2t. So I have negative 16a cosine 2t minus 8b cosine 2t. Do you agree with that? Just combining my cosines. And then if I do my sines, negative 4b minus plus 8a minus 12b, so I have negative 16b.
Wouldn't there also be a minus sine 2t, or just not get shifted over?
No, leave that, because that's what it equals. Oh, I lost my train of thought. What am I doing? Negative 16b sine of 2t. 2t plus 8a sine 2t. Somebody needs to correct me if I lost something. Equals sine of 2t.
I don't know what they were eating.
So that's, I have a negative 4b here, and then a negative 12 times b there. Do you see that negative 12? It gets distributed in. So I get negative 16b. Okay, now using that same idea as above, if I deal with my cosines, and I rewrite this, my cosines that I'm left with, I have negative 16a minus 8b equals 0, because there are 0 cosines. So that's the coefficient that would be in front of cosine. And the coefficient that would be in front of sine, I would have negative 16, let's put this in the same order, actually. I would have positive 8a minus 16b equals 1, because that's the coefficient in front of sine.
Is
This becomes solvable.
that assuming t is 0, or because we get rid of the cosine?
It doesn't matter. I'm saying that what needs to happen for my cosines, there is no cosine in front, so the coefficient needs to be 0. There is a cosine if there is no cosine of 2t. And for my sine of 2t, the coefficient of 8a minus 16b has to be 1, because that's what's there. All right. Solving this one, though, I don't think is as pretty. It looks pretty. Times by 2. So we would get 16a minus 16 times 2 is 32. 32b equals, what did I just multiply by? 2? 2. So I get negative 40b equals 2. So b equals 1/20th, negative. That's a fun number. So negative 16a plus 8/20, 2/5. Is that right? Is that right? 8 times 8 over 20. 4 goes into each. Yes. Okay. Just making sure. I know. Algebra on a Monday. Tricky. So this would be 2/5 equals 16a. So divide by 16. 16 times 5 is 15. 30 is 80. So 2/80. So I get a equals 1/40. And so therefore, all I've done right now is find my particular solution, which says that my a, based on my guess, would be 1/40 cosine 2t. And b was negative 1/20 sine 2t. This is my particular solution. It now needs to be added to my general solution. And my general solution was c1 e to the 6t, because remember we...
The question just asked for the projector.
Oh, did it?
Yeah.
Oh, beautiful. Then we're done. I was ready to write the whole thing. We're done. This is what the whole equation would look like, though.
So how do we guess correctly?
Oh, how do we guess correctly? You don't like this game of just trying?
Yeah, I don't know.
You hope there's a pattern?
There's been no
I
pattern.
bet there's no pattern.
So
I'm going to make you try one more before I give you any pattern. Why? Because I love you guys so much.
my brain that I don't have one of these.
Oh,
True.
The derivative rules when you first learned definition of derivative.
Oh.
Yeah.
What is that? The limit?
The limit as h, whatever you want to call it.
No, it's x approaches 0. times
H
delta
approaches
H.
0.
I thought it was times delta H, right? Something was times delta H.
It's like X over.
F of x plus h minus f of x over h, and the limit is h approaches 0. All right, but now you know your
F of
derivative
x
rules,
plus
right?
h minus f of x over h as h approaches 0.
All right. Okay. Before we get too far, we already know the complementary solution because this is the same problem we did before. So, you're welcome for keeping these simple. Simpler. They're not simple. There's nothing simple about these.
The word problem, like the temperature of the turkey.
With Mr. Myers?
Yeah. And then you always got mad at us for like the smallest grammar mistakes.
Sure.
Grammar mistakes.
I don't remember
He was very particular about grading because it was either right or wrong.
No, he was like, if you wouldn't word it the right way.
Yeah,
But
he
it was
wouldn't
that
give you
one theorem. Or yeah, you had
There's a
to
couple
fix it,
things
and
where
this
you
is
had to
the
actually
order.
walk through the
Let's finish this fourth example and then let's go back and come up with some general rules of how we can make good guesses for that particular solution. Okay. We already know the complementary solution because we're using the exact same thing. But if we were to guess at a general solution here, or at a particular solution here, what might you guess? Any thoughts as to what you might guess for a particular solution? Based on the fact that the what this function equals, that g of t is 2t cubed minus t plus 3.
some polynomial function
Some polynomial function, I agree.
of the third degree
Of the third degree, I also agree.
with a constant equal to 3.
With a constant equal to 3, okay. Do we need to include all powers?
Yes.
Yes. So the particular solution I would guess at for this would be something in the form of at cubed plus bt squared.
You know what a is pretty quick, though.
We do know what a should be. Why?
Because when you take the derivative of a polynomial, you always get rid of a degree. So if you have a t cubed and there's a t cubed, then the only place it will appear is in the y term. So you can just demonstrate that it's negative 1/6.
It is negative 1/6. I'm not sure everybody followed that.
Okay, well, every time you take a derivative of it, it goes down a part.
Oh.
Agreed.
Yeah.
So the only place we'll ever see a t cubed
Is in the original.
is in the original.
Yep.
The only place where that appears is in negative 12 times the original.
Right.
And we know that has to be equal to 2t cubed.
Yes.
So negative 12 times some value is equal to 2.
Perfect. Okay, so where Jake went with that, and maybe you don't see that connection right away, and I can show you, we can walk through it regardless. What Jake is saying is the only time we will ever have a t cubed as part of our particular solution is before taking the derivatives, right? So that would be what our function is at y, the function of y. And we know that the t cubed coefficient has to be 2 because that's what's given to us. And so if we say that when we multiply that by negative 12, we're going to end up with that whole expression would be multiplied by negative 12. So we'd have negative 12at cubed has to equal 2t cubed, which means a would have to be negative 1/6. He's not wrong. You may not see that right away. That may not be something that jumps out at you necessarily. So you can go through the same process we've gone through, which is taking the derivatives of this guess, 2b plus c. That would be y prime, and y double prime then would be 6at plus 2b. And if we substitute all of this in, it gets real messy real quick. So we would have 6at plus 2b minus 4 times 3at squared plus 2bt plus c minus 12, and y is the at cubed plus bt squared plus ct plus d. And all of that needs to equal 2t cubed minus t plus 3. So my goal now is to gather all of my like terms. So let's see what we have. When we gather any like terms, well, let's just...
Oh, I think it's
minus 8 bt minus 4c minus 12at cubed minus 12bt squared minus 12ct minus 12d equals this 2t cubed minus t plus 3. Okay, so gathering like terms. What I'm looking for are my variables, the t, because I'm trying to solve for the coefficients. That's why this is called the method of the undetermined coefficients. That's what we're solving for. So starting with my t cubed, the only t cubed I have is this negative 12a t cubed, which has to equal 2t cubed. And that's where Jake was explaining that that would be the only time we're going to get t cubed is before taking derivatives. So a has to be negative 1/6. Now, if we start to gather other like terms, let's see, let's go to t squared. I don't have any t squared on the other side, but I do have negative 12a and negative 12b. So negative 12a t squared minus 12b t squared equals 0 t squared because there isn't a t squared. So we get negative 12a minus 12b equals 0. Knowing that a is negative 1/6, though, would we get a equals negative 1/6? My gosh, you said it was a long day. Why can I 12 divided by 6 is 2? 2. It's 2. And so then b happens to be negative 12 equals, or 12b equals 2. So b equals negative 1/6 as well. Yep, it would be positive because this would be negative. Thank you. All right, let's gather the next t we actually have. So 6at minus 8bt minus 12ct. So 6at minus 8bt minus 12ct has to equal negative t, right? Did I lose one? Are we good? Now, we know a, so this would give me negative t minus 8/6, that's fantastic, 8/6t, probably could have reduced that, minus 12ct equals negative t. So really I just want negative 1 minus 8/6 minus 12c equals negative 1. Deal with all my t's, pull all my t's out. Oh goodness. Okay, so what? The ones cancel. So we get negative 12c equals positive, probably could reduce that, 4/3, divide by negative 12. Oh, divide. What would that be? So that'd be 36, 4/36 negative, so negative 1/9. Yeah, is that good?
Yeah, I just did it. I thought about it.
Negative 2b, negative 4c, negative 12d has to equal 3. So 2b minus 4c minus 12d equals 3. We know b and c, also not pretty. So we get 2/6, so 1/3 minus plus 4/9 minus 12d equals 3. Times by 3, 7/9. That's an ugly fraction. Solving for d now, we get 12d, negative 12d. 29th, thank you. I'm glad someone's awake. Divide by 12, we would get d equals to 10, negative 5 over 27, right? Check that.
Divide by 2. gives
Divide by
you
4.
3.
You could divide by 4.
Okay. Divide by 4, then divide by 3.
So it'd be 3 times 9 and then
Times 9, 20 divided by 4 is 5.
5. Yeah?
527.
Yeah.
Negative.
Yep. Okay. So this question again asked only for the particular solution. We already knew the complementary solution. So the particular solution now then would be the y of p would equal negative 1/6 t cubed, a t cubed, plus b t squared minus 1/9 t minus 5/27. So a t cubed plus bt squared plus ct plus d. That would be our particular solution. So if we wanted to find the general solution, I did not ask you for this, but my general solution for this would be the complementary solution plus all of this particular solution. 1/9 t minus 5/27. Yeah. So this would be my general solution. Now, really all I asked you for was the complementary solution, or sorry, the particular solution, not the general solution, which is that part. Yeah.
And just to be clear, the particular solution without the complementary solutions is a solution of the equation.
It is a solution of the
But
equation.
the complementary solutions without the particular solution are not a solution of the equation because they'll always equal 0.
Correct.
Okay, so we just add them to give more knowledge.
Yes.
Okay.
Yeah. Yeah, the particular solution works on its own.
Okay.
It stands alone.
But the complementary solutions will always, they'll never work if g of t is not 0.
Correct. The complementary solutions wouldn't work unless it is assumed that it is homogeneous at some point.
Yeah.
Yep. Complementary, remember, complementary are these ones, the part we get assuming the function equals 0. And then the particular is what we get when...
And then there's that fun block that just lets us add solutions whenever
Yes.
we feel like it.
The principle of superposition, which allows us to add the solutions together. Yep. Okay. So we've looked at 3 types of functions so far. And we've made guesses based on that. So let's solidify what our the good guesses should be. I'm going to use good in quotes because there are other things that will work. But let's talk about just our good solutions. So we looked at when our g of t was e raised to the rt. And the guess that we used was some constant e raised to the rt. And that worked well.
If we ever had a function of like e to the f of t, would we just guess k e to the f of t?
That's a good question. So you're saying it's a function, like the e
Yeah.
raised to a function,
Yeah.
other than just t?
Yeah, we just guess that how it
You would have to have a chain in there somewhere.
Okay, well f prime e to the
We would need an...
kf prime.
Yes.
Okay.
We would need that.
No thanks.
No thanks. Well, let's say we looked at one that was it a sine or cosine? I don't remember.
Well, it was a sine.
Was it?
We ended up using cosine.
Okay. So when we have a sine of some,
Alpha t.
yeah, let's do alpha t. Remember we said that we would have to multiply by some constant sine alpha t, but plus b cosine some alpha t. Now we didn't talk about cosine. What do you think about if it was just cosine alpha t?
Well, minus is influenced by the constant, so the same.
So it'd be the same. Why? Even though when we take derivatives of cosine, we end up with negatives. Well, we do with sines as well. But those constants, this constant in the front actually absorbs that negative. We don't need to include it necessarily. So this would be the exact same. Now, what if we change it and we have a sine alpha t plus cosine alpha t? It is the same thing. Okay, so the last thing that we looked at and that we're going to talk about today, and then we're just going to look at, we're not going to solve any, well, we might solve a couple more, I can't remember, was we talked about a polynomial. So let's call it an nth degree polynomial. What was our guess? An nth degree polynomial. So if we have to include all terms, polynomial. These are going to be the best guesses that we have. There are others that we could look at. These are going to be the ones we'll focus on. These come up the most. But we can get lots of combinations of these. They don't have to stay exactly like this. I don't feel like solving for a particular solution at the moment. We're going to look at more complicated functions, but I'm going to skip example 5 for just a moment. Because what I want to do is look at what happens when we have products of solutions and how we might make our guesses. Actually, let's go back to 5 because it will answer the question. We're just not going to solve it at the moment. We already know our complementary solution because this is the exact same question we've been doing the whole time. But if you notice this problem here, the homogeneous part of this problem is a little bit different than we've seen in the past. It's not just e to the kt or e to the rt or whatever it happens to be. It has a t attached to it. So it's a product of a polynomial and an exponential. Okay? When we guess at our particular solution, and if you would like to go ahead and solve this, you can later. I can give you the answer. But if we were to make a guess at our particular solution, if all I had for the homogeneous part was t, what would we guess as our particular solution for that? At plus b. It would be the same degree polynomial that we have there, right? Now, what would we guess if all we had was the e raised to the 4t? What would our particular solution be then? It would be the ke to the 4t. So, when I guess at a particular solution that has a product like this, the guess that I'm going to make, or the one I'm going to assume is going to work, or hopefully works, is going to be the product of the two guesses. Well, I don't do this. I did not come up with these equations. Blame nature.
I think this should use like the phonetic alphabet, so when it's 4t, can we just write 40?
Ask that question again. Sorry, I didn't hear it.
Can we just use the phonetic alphabet, so like 4t would just become 40?
Can you use the phonetic alphabet? Yes. Jack. Too early. It's too early.
I vote we take a nap and circle back to this in about an hour.
Circle back to it in an hour.
Yeah.
Second period.
Yeah.
All right.
I'd rather not go to English. Then I don't have to go take my micro test.
Well, but see, I kind of like my second period because it's my planned period. So I kind of enjoy it. Not that I don't want to see you. All right.
Turn that to a nap as well.
Or you could have your plan while we're napping.
Yeah, there you go.
Okay. When we multiply these, I just want to show you one thing to simplify it a little bit, because if you look at this right now, it becomes pretty hairy. When we distribute that ke to the 4t to both terms, we have kate to the 4. Oh, that's some. Hey, Kate. K40. And then we have. It took me a long time to get that, Jack. Too early. Okay. Now.
How do you pronounce that other name?
Good luck.
Is there supposed to be a T in front of the...
There is no T. That's why I didn't have it originally, but then I was like, the other one has a T. I wasn't thinking. Yes, sorry. KB e to the 4t. Yep. All right. Keep in mind that k was a constant for our term before.
You just use like capital A and capital B.
You can use capital A, capital B. You could give them a whole new name of C and D if you wanted. I don't care what you call these, but I wouldn't work with two constants in that because then we need to solve for both of them. The method of undetermined coefficients asks us to find the coefficients for our terms. I don't want to have to find a K and an A and then multiply them together. So I'm going to just go ahead and rename these. If you want to rename them as capital A and then capital B. Oh my gosh. Too bad Kate's not here. It would be more fun. There we go. That would be what we would guess at our particular solution, and then we would go through and solve. Okay, so here's what I want you to do. There are several examples down below, A, B, C, where we want to see or figure out what our guess might be for the particular solutions. So let's assume this is the homogeneous part. I don't care about the complementary solution right now. We're just saying what we would choose as our guess. So I want you to think about these three examples and see what you would list as your guess. And I wouldn't multiply them all out necessarily. So let's start there and just see what you would get for the guess, because the multiplication of our particular solutions is actually the easier part. We get to the adding, it gets a little bit messier. What? You don't want to do that problem?
No.
That sounded like an evil laugh.
No, I would not give you that problem. Could it come up in some of your major classes? Sure. At that point, they might allow you to use computer software. I don't know.
Be a lot cooler if it did.
It's a lot of things. All right. For one is very similar to the last, or A, it's A, is very similar to the last one. So we would take that 16e to the 7t, and that would be our ke to the 7t. And then that sine of 10t, this portion, would be a sine 10t, b cos 10t. Do we do okay with that? They do expand. They get messy real quick. All right, what about the next one? And yes, when you multiply those through, if you were to multiply those through, we would end up with new constants because we would end up in the same scenario we had before where we had a K and an A multiplied together. Give them a new name or just call them capital A, or they are capital A now. Call them little k a and know that's what you're solving for. Are those...
What kind of constants can we use Greek letters?
Use Greek letters. Use...
Can we use like smiley face?
Sure, use the smiley face, heart. It would be hard to keep track of, I think, but what about this next one? What would it look like? Oh, we wouldn't want to all talk at once. That'd be too much.
I don't think we want to talk at all.
AT squared plus BT plus C.
And then times
And you can name those constants whatever you want, really. All right, what about the C?
Lot of constants.
Does it make you sad? Happy? Stressed?
Yeah, last
All
one.
of the above.
Solve for it, so it's like.
I'm not asking you to solve for this. Not at this juncture.
Is that gonna be like March or April?
No. K e to the negative 2t times what? At plus b times
Big A, sine 90, cosine whatever.
cosine. Yeah, it doesn't really matter which one goes first. Plus. And there are, when we multiply that through, that would be a lot of foiling going on there. A lot of constants. Give them a new name. Don't multiply it, just call it good. Questions so far? All right, sure. You give them a name. Fred. George. Yep.
Is that enough for today?
No, the next one's easy. It's just superposition. You just add stuff.
Jake saying it's easy does not inspire confidence.
Okay, not okay. Probably algebraically it's a pain,
It would be a pain to do independently, yes.
but like the concept is way easier than this multiplication stuff.
Good.
How bad is the homework?
Not bad. It's, well, I took off one of the questions that I thought was really bad, and I haven't finished two of them. So if those end up being really bad, then we're in trouble.
What if you just like one problem because they're long enough?
Some actual names.
Go through the whole Harry Potter cast if we want. Yep, happy to.
It's actually fair.
Am I good to go on? Okay. Let's talk about the sum. Actually, you'll like the sum a bit better. So if a particular solution is a particular solution for one of our functions, and we have a particular solution for another function, but we, in our problem, have those two functions, g1 of t, g2 of t, added together, then the particular solution is just the sum. Okay? So don't panic about this example that we're about to do, because you've done it all before. Okay? If you look back at your notes, you will see that we already did this y double prime minus 4y prime minus 12y. We have found that one several times, right? What we've also found is this sum here, 3e to the 5t. That was the first example we did. And we said that that particular solution, so if our g1 of t is this 3e to the 5t, from example 1, I think, we said our particular solution for this one, say that again, what was it? Negative 3/7 e to the 5t. That's what we got. Do you remember? That was from example 1. And we've already done the sine of 2t. That was from example 1. So if our g2 of t is the sine of 2t, oh, sorry, example 2, our particular solution for this problem was fun, right? It was like
1/30 cosine of 2t, minus 1/20 sine of 2t.
that was fun.
Plus the one that we didn't do.
Plus the one that we didn't do, I'll happily give you that answer. Plus this one that we didn't do. Now, I will tell you from example, we didn't do this one. If g3 of t is te to the 4t, we didn't finish it on the last page, but the particular solution that we would have come up with, because we had an initial value there, was negative 1/12 t e to the 4t minus 1/36 e to the 4t would have been our particular solution. So this is example 1. This was example 3. This was example 5. If you want to go back and look at those. So what we can say now when we're adding them, our particular solution would be the sum of all of these together.
Does that mean the general is still still just like the first plus all that.
Yep,
Okay.
it's exactly right.
So
So-
as well as solving these,
Yep.
would we make a guess that's all of those at once, or would we do it one at a time? Which one's easier?
Well, I'm not a glutton for punishment, like some people are. You could do it all at once. I don't think it would be worth it. I think it would be worth it to break them apart
Okay.
and focus on, we already know what the complementary solution is going to be.
Yeah.
It's the same for all of them. I don't have to worry about that. So then I would deal with the particular solution, and our derivatives will be different every time. So I would focus on, I mean, if you think about trying to find, right, like if we guessed at this, we would guess k e to the 5t out a
Plus-
cosine,
Yeah.
right? And to take the derivative of that and then plug it in,
Okay.
I don't know that that's worth
Probably
it to
not,
me.
not with solving them simultaneously.
I would not try to solve them simultaneously unless you really want to go through.
No.
If you do that, will you get this answer or will it look a little different?
Now, I didn't, to be honest on this one, we didn't have particular solutions, or sorry, initial values. No initial values were given. So all we could come up with would be the general, like, I can't use general in that case. All we would come up with would be the solution, the particular solution without the initial values. Which makes it a little bit messier. Oh, that would be more for the other part. No, we'd come up with this eventually.
Okay.
It would just take ages. It would take
Ages and pages, both.
It would take you the time it took you to do 1, and then 3, and then 5, and then all the mistakes you made there.
Yes, and assuming you don't, yeah.
Is it possible that guess could be wrong too? Or would that-
Oh,
No.
please don't say that.
If that is part of our homogeneous solution, the guess will work. Could there be other guesses that also work? Yes.
Is there like with these, like in the table we got, are those like not guesses? Those are like tried and true, always gonna work? Or are there still situations where those won't work?
That's a good question.
It feels like for the ones that we've discussed, trigonometric functions, polynomials,
They're gonna work.
e to the t, it'll
I can't
always
think of an
work.
example where they don't work, and I've not seen one where it comes up and it's like, oh yeah, just kidding, the guess we've told you works all the time except for this one.
Okay.
So I haven't seen it. Now,
Families of functions that have guesses that work sometimes. But
yes,
those
I would have,
feel
yes.
like they work all the time.
These are the ones that are consistent. So if we were to guess at some of these differential equations, that's just looking at what we would make a guess for. I might skip that. It gets messy. Okay. If we were to go through some of these guesses that are on here, it gets real messy real quick. Like, for example, when we separate them, I think the weirdest one might be if they are not in sequential order, maybe. So let's look at, just for example, D. I want to look at D and I want to look at F because F is pretty messy. Yeah, F is pretty messy. Okay. So let's look at D first. I just want you to pay attention to the fact, it's weird that mine is on a different page than yours. I want you to pay attention to the fact that although this is broken up, this is still a polynomial because this could be rewritten as 6t squared plus 9, and then minus the 7 sine 3t. So when we're dealing with problems like this, if we were to guess at a particular solution here, my first guess would include the entire polynomial, which would be the at squared plus bt plus c. And my next guess would include the a cosine 3t plus b sine 3t. So that one's pretty, just different. We need to separate it a little bit.
On A,
Uh-huh.
if you were to do that one,
Do we need to do it twice?
right, and then would it be A sine, like
6t
plus or minus B?
plus b. Because even if minus, Okay, so let's say you put minus in there. When you solve it, you're going to end up getting a b that it'll work itself out. So I would put a plus, just because we like positive numbers better. All right, let's look at F real quick. It's a mess. Do we see it? There's 2 parts to this, 3 parts to this on F. 4 parts.
Simplify, though, like to some nicer constant.
It does simplify to not terrible constants, but it looks messy to begin with. There are 2 parts here. And each of these 2 parts has a multiplication. So within this t squared cos t, I actually have to put a guess in for the t squared part, which would include at squared plus bt plus c. That would be the guess for the t squared. And then for the cosine of t, we would have a cos, that's just t, plus b sine t. And this would be the particular solution guess for just that part. Okay? And then we have the negative 5t sine t. And then we would need a guess for this part as well. And so for the 5t, I'm going to put a plus in there. That's fine, because that'll be absorbed if it needs it. For that 5t, my guess would be, I'm going to need another constant in there. I don't know. dt plus f. I didn't ask you to. I'm just saying this is what it would be. Multiplied by, let's give another constant. Well, we've used d. We've used c. Well, give it another name. Why not? And this part would be the guess here. Okay, so can we make the guess? Okay, am I going to ask you to solve this? No, I'm not. But I'm saying if we were to make a guess on solving this, my solution, my particular solution would have to fit this form.
Well, couldn't it also fit the form of at squared plus bt plus c? Just like that top part?
Yes.
Just all the lower constants, just kind of vaguely combine it.
Okay, so Jake has a point there. Did you hear his point? Not understanding is totally fine. If you look at this top part here, right? And we look down here. When we start foiling, if we were to foil these out and combine them, what would we see? Well, we would see an at squared, a bt, a c, whatever the constant is, multiplied by this, but we'd also have a t term here and a constant here multiplied by a cosine and sine with the t also. Wouldn't they just be able to combine to be one expression? So really, in a situation like this, we don't really need this portion because it will end up being absorbed up here. Do you see why? These same terms, dt times m cosine t, when we multiply those, we'll also have a similar or like term when we multiply the top two. Now, we can't cancel out the top part because it's got an at squared and we need that part. But yes, we can vaguely ignore that second piece. Looks messy to begin with, but vaguely ignore it because it'll get absorbed.
You're just gonna hand wave it away.
Yeah, pretty much. Sleight of hand trick. Yep. Truthy.
Like negative 5t sine this alpha t.
Yes, if it was a different.
So it'll, yeah. You have
So
to,
if this argument for sine was different, like if it were sine of 5t, and this was cosine 5t, sine 5t, then we could not get rid of it. It's because that when multiplied, these will all be the same. Our like terms will just combine nicely. But great question, if it had not been the same. All right.
Are we done?
Are you done? Do you see how many more pages there are? What is going on?
I think we need at least 2 more reads.
Okay. Are we done? Yeah. Okay.